IBM systems. I work on optimizing libraries for Linux, mostly focusing on AI libraries. And today we also have another speaker, Satish. Satish, would you like to introduce?
Yeah, sure, Raji. This is Satish here. I work for IBM Systems as well. I'm the performance architect for power systems, and I look after the workload characterization and hardware design guidance team in IBM. So today we'll be looking into some of the libraries and performance aspects of matrix math assist architecture, what we have introduced as part of Power ISA. So Raji, over to you.
Yep, sure. So MMA stands for Matrix Multiply Assist, and this is a new feature added in POWER10. And in last year's Open Power Summit, Satish has talked about the internals, the basics of MMA, and today's talk is going to be about enabling MMA in the compilers and the libraries side. So those who want to look at the basics of the internals of MMA can refer to the last year's presentation. And then after I talk about the enablement, I'll let Satish talk about the performance aspects of it. What is it impacting, how the workloads are showing the same performance improvements. So MMA stands for Matrix Multiply Assist. As I said, this is a new feature that is added in Power ISA v3.1. This particular feature adds a new set of instructions to support the dense matrix math operations. Today, if we look at some of the training or inferencing algorithms in neural network, they all require some form of matrix multiplication. And even in one of the algorithms, it shows more than 85% of time is spent on the matrix multiplication that is commonly called as GEM. GEM stands for General Matrix to Matrix Multiplication. And there are different set of libraries that enable or that implement these linear algebra operations. So these MMA instructions are going to help in the efficient implementations for the key algorithm in both machine learning and deep learning side. And now that it is available on the Power ISA and on the POWER10 hardware, the next step was to enable it on the compilers and the libraries to make use of it. So this is about the linear algebra and the POWER10 ISA. BLAS stands for Basic Linear Algebra Subprograms. Today, there are different set of libraries that implement these linear algebra operations, and there are different set of functions for that. So the most commonly used libraries are OpenBLAS and Eigen, and they are the default underlying library for many of the MLDL frameworks. So on the blue color box here on the left-hand side, this is a simple stack where we have POWER10 hardware at the bottom, and then there are different set of linear algebra libraries that can be installed on the Linux system. Some of them are OpenBLAS, BLIS, Eigen, and MLAS. MLAS stands for Microsoft Linear Algebra Subprograms, and that is used in the ONNXRuntime. And PyTorch, and above that layer, we have the frameworks where we have PyTorch, TensorFlow, and ONNXRuntime. These are different set of AI frameworks that make use of the underlying libraries implementation. And on the right-hand side, this is some of the examples of the new MMA instructions that are added in POWER10. I have listed only a few of it, but there are many more data types like double, float 32, B float 16, float 16, int 8, int 16, and int 4. So the input for all these GER instructions or accumulator. Accumulators are new there are new 8 set of 512-bit registers added. Those are called accumulators, and they are used to store the result of these matrix multiplication. And depending on the data type, the accumulators can vary from 4x4 or 4x2 matrix. And X and Y here are the inputs. And depending on the data type of the GER instruction, it varies from 4x1 to 4x2. This one particular instruction is going to do 16 different multiplication. And that is shown in the bottom picture where this is a single precision 4x4 compute array, where the input is going to be 4 float numbers from the first matrix and then 4 numbers from the second matrix. And each number gets multiplied to the other 4, and it produces 16 different results. And the result is now it is a 4x4 float 32 array, and it will be stored in a data type called accumulator. It's a vector quad type. It's a 512-bit register, and the accumulators are used to store the results of these matrix multiplication, and they are used for accumulating for each and every multiplication operation. So let's get into the compiler support for this. There are different built-ins added to enable this MMA for Power10. I have listed some of them in this table, and a detailed version or the detailed list is available in the link that is shown below. This MMA support is added in both GCC and Clang from the version GCC 10 and Clang 12. Let's look at some of the built-in types here. The first one is vector quad, which is a data type that is used to talk about the accumulator, which is used for storing the results of the matrix multiplication. And then the next one is set axi. This is used to reset the accumulators, because before we get into the inner loop of the multiplication loop, we have to set the accumulator values to 0, and this is used for that particular purpose. And then there are different assemble and disassemble accumulators where we can use to merge different elements into the accumulator, or after doing all the multiplication, we have to get the results from the accumulator. So that is the disassemble part of it. And there are also MMA built-ins for each of the GER instructions that are added in Power10. As I said, the detailed list is here, and most of them starts with built-in MMA XDF, and then depending on the data type, it will be like F32 or F64, or sometimes it is I8. And then followed by GER, it's the star, the second star represents the rank K update. That means how many rows this particular instruction is going to update on the result matrix. And the last one is the build pair and the disassemble pair. In Power10, we have a new vector pair type of instruction that is used for dgem in this particular multiplication. And to generate a pair, we can use build pair or disassemble pair related built-ins. This is one of a simple example to show how to use these MMA built-ins. As I said, vector quad is a data type that we use to represent an accumulator. And then set axi is used to zero out the accumulator. So before we get into the loop, it is better to zero out the results so that we get, even if there are any old results in the accumulator, we can just zero out. And in the inner loop, we have MMA built-ins, which are used to multiply two inputs. So in this case, EFI and BFI are, they both get multiplied and the results are stored in AX0. And when it comes for the second time in the loop, the same results, the multiplied result gets added to the previous result. And once the inner loop is done, we use this MMA disassemble accumulator built-in, which is used to restore the result. I mean, we can, this particular built-in says that get all the results from accumulator 0 and put it into my result matrix. So now that we talked about the compiler side of it, I'm going to talk now about the libraries part of it, where we have picked multiple libraries to enable this MMA. The first one is OpenBLAS. As I said, BLAS stands for Basic Linear Algebra Subprograms. And this particular library has different type of linear algebra functions. They are categorized as level 1, level 2, and level 3. In level 1, we have functions to do vector and vector operation. And in level 2, it's matrix and vector. And level 3 is all about matrix operation. So particularly for this MMA, we have added the support for all the float, double, and complex type of gem and TRMM kernels in OpenBLAS. And these are available from 0.3.10 version of OpenBLAS. And then there is an easy integration possible. Most of the libraries like NumPy or frameworks like PyTorch today, they are already integrated with OpenBLAS. So whatever changes that we have added in OpenBLAS, it will be reflected in the frameworks automatically. bfloat16 is a new data type that we have added in OpenBLAS. This is a reduced size and it is highly adopted in MLDL nowadays. OpenBLAS did not support bfloat16 before, and we added support for this particular data type. And there is also Power10 optimized bfloat16 gem kernel available in OpenBLAS from a particular version. And apart from doing MMA related work in OpenBLAS, there are also different optimizations that we had done in the past few months to make use of the Power10 vector pair instructions on the level 1 and level 2 side. When we started to look into this OpenBLAS code for Power9, it was written in assembly. And in order to consider the future designs of MMA, some of the gem kernels are now converted from assembly to built-in so that it will become easy when we do any future alterations of this MMA work. So the next library is Eigen. Eigen is a header-only library written in C++, and this is used in TensorFlow. So we had to make a lot of design changes to accommodate this MMA, particularly in terms of packing. Before we have to multiply a matrix, we have to pack the input data in such a way that it is actually fits into the MMA loop. So the packing, which was there already in Eigen, was not really suitable for MMA, and we had to make a lot of design changes for that, and all those changes went into Eigen 3.4 release. And then we had added the level 3 for complex and real float and double type. We have optimized this gem kernel specifically for Power10 in Eigen code. Apart from the float and double, we also want to focus on the low precision data types like bfloat and int8, bfloat16 and int8, because the low precision is kind of recently it's becoming popular on the DL side, and we want to focus on that as well. So we have some plans to look at enabling bfloat16 in Eigen as well. So the next one is ONNXRuntime. It's a high performance runtime inference engine for ONNX models. Typically in the ONNX workflow, the training is done in different frameworks like PyTorch or TensorFlow, and then it gets converted to a format called ONNX model. It's a generic model which can run on any framework later, and ONNXRuntime is one of the inference engine for that. So in that we have linear algebra code called as MLAS library, and we added single precision float 32 optimization for Power10 using MMA in ONNXRuntime recently. And we also want to add DGEM support. Recently, we added the float 64 optimization for Power9 in ONNXRuntime. So those who want to try ONNXRuntime can take the models from ONNXZoo and then run it with ONNXRuntime inference engine. And if it is on a Power10 system, they can make use of this MMA through the MLAS library. So this is a quick summary of what we have optimized so far on the library side. This lists the name of the library, the link to get this library. As I said, these are all open source libraries, and from a particular version, the MMA optimizations are available. For OpenBLAS, it's from 0.3.11, and for Eigen, it is from 3.4. So one good thing about all these libraries is they have this dynamic CPU detection. Depending on where this particular library is running, it can automatically detect the processor type and take the appropriate optimization. For example, if OpenBLAS even if it is built on Power9 system, and if it is moved to Power10 system, it is capable of detecting the hardware and pick up MMA depending on the processor type. So there are the level 1, 2, 3 functions in OpenBLAS. We have optimized all the gem with MMA in OpenBLAS. And on level 2, we try to use MMA for some of the GemV functions as well. And today the GemV in OpenBLAS also uses MMA functionality. And other than that, Power10 vector pair instructions, load store vector pair instructions are also used on some of these functions. BLIS is another library where we had added this MMA capability, and for the low precision support, since BLIS is not yet enabled the infrastructure for that, it is right now residing in a sandbox. So those who want to try the low precision MMA capability can still compile BLIS using the sandbox. There is a README in the BLIS repository which shows how to build BLIS and then try out these low precision kernels as well. And ONNXRuntime is the fourth one where we had added MMA in SGEM code, and it is available from the latest release 190. So now that I talked about the compilers and then the libraries part of it, this is about the AI frameworks. If someone wants to try out this P10 MMA with PyTorch or TensorFlow, there are already pre-built packages available in one of the Conda channel called Rocket CE, where we can do a Conda install -c Rocket CE and then PyTorch. This will automatically install the PyTorch and the OpenBLAS with P10 MMA capabilities. So with this, I will stop here, and then Satish will talk about the performance aspects of it. Satish. Satish, you're on mute. I'm not able to hear you. Okay, looks like Satish wants permission to unmute.
Okay, I got it now.
Okay.
Sorry, I didn't realize that I will not have permission to unmute. Okay, thanks, Raji. That was a good summary of what we have done on the ISA front, libraries front, compiler front, and also in terms of enabling and making it available to the community, right? How they can leverage MMA. So I'm going to take one step further and talk about some of the hardware capabilities. We have touched base on all of these things in the last OpenBLAS presentation. But right now, given that all these libraries are enabled, right, we are kind of experimenting a lot of these real DL models and trying to understand what performance the POWER10 hardware can deliver, given that we have increased the core count, the core strength, and the bandwidths across different cache levels and all the way up to memory. So just to give a quick recap, the POWER10 SMT8 core. I'll also talk about what type of modules we are introducing on POWER10, and then I'll jump into the performance aspect in the next slide. So before that, from the core aspect, in general, we have doubled the SIMD capability. So if you want to compare against POWER9, it has 228-bit compute capability. And with POWER10 on a small core, and then we have doubled it to 4, and on a big core level, we have 8 VSX compute capability. That is 8 independent SIMD engines per core. And with that comes these additional 4 matrix math acceleration units, what's called MMA. So we have a 4 512-bit engines per core, per big core, and that gets you a huge compute capability, right, with the hardware. So a single core of POWER10 has all this thing built in into the core. So certainly, as we increase the compute capabilities, we have to make sure that we get the right level of bandwidth to feed these things, right, into for the data. From the data perspective, we have to feed the data to these units. So we have doubled the bandwidth across all the levels, right, all the way from L1, L2, L3, and all the way up to memory. And we also have introduced some new concepts around fusion. If you recap to our hot chips presentation we did like a couple of years back, last year, right? So we have talked about a lot of these capabilities around fusion, on how 2 loads can go together and get fused internally in the microarchitecture, and the 2 stores can get fused. All that will be covered. So all these things was kind of holistically done in order to support both the microarchitecture improvement as well as to support the AI and FP capabilities, what is coming along with this hardware. So Raji has already shown this table in terms of flops capabilities, what we are bringing on board as alongside the POWER10 other features. So it supports all different data types, all the way from 64 all the way up to int4, though int4 is still an experimental phase, right? A lot of research and academia are trying out on how to leverage it. We already have it in the hardware. As we go to our future, right, we certainly can leverage the compute capabilities of int4 as well. So it certainly opens up a lot of ways for innovation and trying out new things with this hardware and see where we can, right, exploit all these benefits, what we could get out of this reduction in the data types. So that's about our P10 hardware. And if you look at the P10 chip, I don't have a slide here, but I'll just give a quick intro of what we have in the chip. We have introduced two chips in hot chips, right? One is called single chip module. The other one is a dual chip module. The single chip module comes with a maximum core count of 15 big cores, and the dual chip module comes with a maximum core count of up to 30 big cores. So if you want to compare against P9, P9 has a maximum core count of 12 big cores. So certainly there is a huge amount of core increase happening right now on Power 10. The single chip module is primarily designed for like accelerating the single thread and low core count requirements. And then the DCM is more about throughput and high compute requirements. So that's where we have positioned both of our chips. And if you go to the next slide, Raji, I'd like to touch base on the recent system, what we have announced with P10. Can we go to the next slide, please? Okay, so we have recently announced this Power 10 based systems called E1080, which is a Power 10 system with which has the 15 core modules, the SCM modules in there, the single chip modules. And what we have done with that system is, I mean, whatever Raji has talked about, right, in terms of enabling all these open source libraries. And there's nothing proprietary here. Everything is open source, and we got all the capabilities built into this to exploit this, the big AI inferencing capability, which is sitting on the core. And we took that libraries, we took the framework, what Raji has talked about, and we tried few models, right, to see whatever claims we have made in the hot chips, whether to kind of showcase it to our to all the folks who love Power architecture, right? How does it stand, right? So in terms of performance, we run the BERT model on PyTorch, which uses OpenBLAS, the library what Raji just spoke about with FP32 capability. And we were able to kind of see a throughput increase of 5x. So in terms of core count, we are just moving from 12 core to 15 core, just a 3 additional cores you see in Power 10. But in terms of performance boost, what we get at the same FP32 level, we're not going lower precision yet, right? This particular improvement is coming at single precision. So it means like Power 9 has a huge single precision capability, and over that, now we are moving to Power 10 with this MMA, we get this huge boost of 5x. And I also talked about our dual chip module, which has support for up to 30 cores. And we are also looking at some of the optimizations in this space. So with that, with the same precision level of moving from Power 9 to Power 10, right, single precision, you can certainly get much more gains. And over that, we have all the gains coming from quantization of moving to the lower precision. So the net to net is lots of AI capability we have put into this core, and we have built the system. And this is primarily to enable our customers to leverage all their inference needs along with their enterprise workflows, and don't have to rely too much upon the external accelerators, right? Certainly there are values doing that, but a lot of the stuff can be done we were using this in-core AI acceleration engine. So that's where we are, and we are looking at more options and enabling more such libraries and enabling more precision levels as we go forward, whichever takes more traction in the market and whatever customer is looking for, right? We obviously will be working towards that and get those things enabled to fulfill all the AI needs for the future. So with that, I think this slide mostly gives the references. I think that's all we have for today. I think we covered most of it, right, Raji? There any
Yes.
other slide? Okay, I think we are done. Thank you. Thanks. If you have any questions, we can take few now, and feel free to reach out to us offline as well for any questions you have. Okay, any questions that we could take?
Okay, if there are no questions, then we can end this session. Thanks everyone for joining.
Thank you. Thanks everyone. Bye-bye.